Okay, then I think we'll get started with this unit. I don't think it's going to be too long. So in the what we did yesterday, we first looked at some sort of modeling in general, an introduction, and then looked at a few specific simple models. And so this is just going to be an overview of how, in general, you can use these kind of models, or what types of questions you can answer. This is a categorization I like. There's, of course, many other ways you can put them into categories, but it's maybe useful to think about it. And then in the exercises, you can look at specific examples for all of those. So this is a diagram which I'm sure you've seen by now, since you probably looked at that review paper that we keep mentioning throughout the reading. So here's sort of three distinct ways that you can think of using the models. As you'll realize when we talk through it and you go, this distinction is mostly conceptual. When you actually do it, you quite likely combine them, but it's still good to think of them. And of course, usually when you do a project, you use more than one approach. You might combine them, either all three or two of the three. Sometimes you do one explicitly and the other sort of on the side. But we'll walk through them now. We'll start with the exploration and then do prediction and fitting. And I'll put that slide up every so often so we can go back and look at how they all connect with each other. So the exploration is really the first step when you have a new system. You're not sure yet what's going on in the system. You're building a model. You're using a model to explore the system and have some ideas. I'm walking through it using an example that's from a recent paper. It's not exactly that model, but very close. And in fact, it's a model you could explore yourself if you use one of the models in DSARM, which is the one with the virus and immune response. The difference here is that we're assuming it's not an actually replicating virus, but that it's a vaccine, so it's killed. So in the virus equation, the only thing that can happen is whatever you stick in initially decays at some rate, and then it's also cleared by antibodies. But so basically, if you use that model and you set the production of virus and the infection rate to 0, you would get this kind of model here. So we have virus or antigen that's initially given. And the question is, how does the dose you give of antigen affect antibodies at the end of the vaccination? That's an important question because we want to, and it actually came up in a discussion yesterday, we want to give enough that we can induce a strong immune response, but we don't want to give more than we need to because we might have shortages. Good example right now with any upcoming coronavirus vaccine will have initially shortages. And also, if you give more, you could potentially have more side effects. So how to do that right? And so that was sort of the question, and I was trying to explore that in broad terms by building a model. So we built this model here, and then we can run this model. In this case, what I'm interested in is the dose. So I keep all the other parameters fixed to values that I think are reasonable, and then run for the model for different doses. And so you get then these kind of curves. It's the same as if you press the run button in the DSARM app multiple times for different settings, and each time you get a different curve. Just plot here. So we can see here, okay, if we change the dose, what happens to the outcomes? Here I'm not plotting well, actually, in this case, I have 4, so I am plotting all 4 variables. So you see the antigen, it does what you think it does. It starts and then just decays. Innate response kicks in pretty quickly and then also decays, and B cells and antibodies ramp up and then basically kind of level off. And so you can just sort of look here, if you look at the dose that would be initially at day 0, the antigen load, and then you could look at the outcome, the antibodies at the end of the infection, that would be here 200 hours. You could read that off. But of course, we can go through that process more systematically. So sometimes you want to look at the time series, and you usually always want to do that if you test your model and try to make sure it works. But then often you're not interested in the whole time series, but more in some quantity. For instance, in this case, the antibodies at the end. Or you could say, I want to know what the total pathogen load is, or what the steady state value for the immune response is. So you're interested in some outcomes, and then you want to see how they vary with some model parameters. So in this case, we wanted to know how antibody levels vary with vaccine dose. And so we also want to know then not just the antibody levels, but how that affects protection. So what do we need to answer that question? Well, we need to choose different levels of the input, in this case, vaccine dose, run the model for each one, record the quantity we are interested in, and basically store the input and the output, and then later we can plot them. So, algorithmically, you go through these steps here. You choose some starting values, run the model, record the quantities, and then you do it again and again until you have a fine enough grid. If you have a simple model, you can run it pretty quickly. You can, choose 100 income-outcome pairs. If you have a more complex model that takes long to run, you might be limited to fewer income-outcome pairs. But basically, you want to get enough so when you plot them, you get basically the whole distribution. If you see there's some kind of areas where it's not clear what the results are, you might want to increase the data points. So here's an example of doing this. You run the model for different doses. You record the antibodies at the end. And in this case, I was interested in protection. And so from the literature, there has been some analysis that looked at antibody levels and how they map onto protection. So it's basically sort of a sigmoid mapping. Initially, there's protection is 0, and then as antibodies increase, protection eventually goes up to 1. And so I just chose some values for these parameters K1 and K2. A is what you get from the model, the antibodies at the end. So you can then compute P. And then I plotted here. So there's the dose, that's the input, the V naught here, and then protection on the on the y-axis. So with this, I was able to explore what is the impact of dose on protection, and nothing surprising shows up here. As you increase the dose, protection goes up. Excuse me. There's a sort of a linear regime, and then eventually it saturates. If you look at the paper, it's actually more interesting for 2 pathogens that mimic live attenuated ones, where you see you initially get an increase in protection, but then it might slope down again. Here's another example. Details don't matter. If you're interested, you can look at this paper. The whole point is that you have here in this example 2 parameters. In this case, it's for flu and the rate at which the virus binds and is released from cells, here indicated by these parameters K plus and K minus. And then there's some quantity that we defined and computed called virus fitness. It's kind of similar to the total area under the curve of the virus. And we were looking at how does virus fitness depend on these parameters. And in this case, it's visualized by a heat map. So you see there's this regime of K plus and K minus where basically the on and the off rates are in good balance. That means the virus is able to get into the cells, and it's also able later to get back out of the cells. And for that, the strength of the HA and NA, which dictate the binding and the release, has to be sort of in a good balance. I'm showing this here because you can see what you can do when you scan over 2 parameters. Of course, once you want to explore some outcome as a function of more than 2 parameters, you have to decide how to plot it. You could, for instance, do these kind of 2D plots and have the other one at discrete values. Let's say there was a 3rd variable called P. You could P it to be 1, 2, 3, 4, and for each one you make a heat map or plots like that. You can plot slices through, where you have one on the x-axis and then the outcome on the y-axis, and then you plot different lines for different values of parameter combinations. So there are different forms you can do that. Graphically is always a good way to illustrate and show your results. And that is a very common use of models. These kind of exploring a system by building a model, running the model, and seeing what patterns does it produce. Sometimes you have a very simple system in question. You might not even need a model. You know what's going to happen. But quite often, interactions are somewhat complex. It's unclear how they might affect the outcome. Or sometimes you know kind of the direction, but you might not know in what shape. So for instance, you say, okay, if we give more drug, we expect faster clearance, but it's unclear, is it going to go down linearly, or do you get initially, if you increase the drug dose, a faster decay, and then it kind of levels off, so at some point more drug doesn't actually help? And those are kind of questions that models are very useful in helping you explore. So if you do that exploration, I told you algorithmically how you do it. If you have something like a graphical interface, you could, click on the buttons and run it multiple times, or you could write some code that basically loops over the parameter you're interested in and runs the model for each one. So if you read through the level 2 section in the tutorial for the DSARM package, it shows you an example like that. There's also apps that in DSARM that already do that for you graphically, so they do the looping for you. So you could look at that code as well to see how that is done. And then, of course, if you want to loop over more than one parameter, you write a loop inside a loop and to scan over all the different parameters.